Bismillahirrahmanirrahim. Good afternoon, everyone. Today, our lecture we will try to solve exercise 7.3 and 7.4. Like we see here at example 7.3, we're dealing with silicon p-n junction at room temperature, has doping concentration of acceptor concentration equal 5 dot exponential 15 and donor concentration equal 5 dot exponential 16. Reverse bias voltage of, that means VR equal to 4 volt is applied. The author wanted from us to determine the bolt barrier potential and width in N region, width in P region, the pleasure region and 2P sides. Yes. Let's start from VBI. We know the appropriate equation to can find the last result about belt barrier potential. This equation is 7.9. VT, like we know, that's mean KT divided on electron and equal 0.0259 ln Na dot Nd divided on intrinsic carrier concentration. Here Ni at room temperature to silicon equal 1.5 dot exponential 10. Yes. Here we calculated it. Belt barrier potential voltage equal 0.718 volts. Now we will use this result to calculate X and width in the pleasure region in N type, in N side, sorry. That's mean if the author didn't ask from us to determine VBI, we must calculate it because without it we can't calculate the last result about width the pleasure region in N side. Here 2 permittivity divided on electron charge 1.6 dot exponential minus 19 between 2 brackets belt barrier potential plus reverse bias voltage between 2 brackets Na divided on Nd, and the last like equation 7.28 we explained this equation and how we could derivative it at the last lectures. Let's complete, let's keep going, and the last result will be dot 1053 dot exponential minus 4, but the units we used it centimeter. To change it to micrometer, just we will dot exponential 4 to be the result like that. And after that, we can use the long equation 7.29, or we can use another easy equation like 7.27. All of these results are right. Here, the width, the pleasure region in P side equal 1.053 micrometer. Or we can use this equation, there will be the same result. Actually, I used that twice, these 2 results to calculate, and after that did comparative between them. The last results are same. After that, let's calculate the total width. Actually, the author didn't ask that, but I solved it. Like we know, the total width equal Xn plus width the pleasure region at P side, and the last result equal 1.1583 micrometer. Or we can use this equation 7.34 to calculate, and the equation like I did, we can say it's near from the first result, or we can say both of them are the same. Now, like at B branch, repeat part A for reverse voltage bias equal 8 volt. That means we calculate all these elements again because VR reverse bias voltage, it's important element. Let's keep going. Silicon at room temperature, NaND is the same. Intrinsic carrier concentration is the same because we're still dealing with the same element. Let's write 7.10. VBI equal VT ln Na dot ND divided on intrinsic carrier concentration square. Let's keep going. The last result to VBI equal dot 718 volt. By using the same equation 7.28 to calculate the width in the depletion region and side will equal dou 0.1432 micrometer, or we can say centimeter with exponential -4. By using this equation, we can benefit from some simple equation like 7.27 to can calculate the width in the P side. The last result equal 1.432 micrometer. By calculating the both of them, Xn and XP will calculate the last result about the total width equal 1. Actually, I calculated by use my calculator, and I found the last result was 1.5752. But the author at the last wrote to us the last result to the total width. It was 1.576. The twice my results it was near from the results at the book, because that I think my process were it was right, because some just all the difference it was .008. Okay, and actually I'm used this app, this great scientific calculator. By using my phone, I can write the equation like in my book, because that all this process I think will be easier. Let's keep going. Now exercise 7.4 will talk about how we can calculate the maximum electric field and the p-n junction by using equation 7.36. Emax equal -2 electron divided on permittivity, bolt barrier potential plus reverse bias voltage, dot between two brackets concentration of electrons dot donors divided on Na plus Nd, all these brackets to force half. And at the same time, if we have the result of the total width, or if we can calculate the result of the total width by directly go to its equation, or by calculate Xn with Xp, we can use equation 7.37 by this equation is -2 volt barrier potential plus reverse bias voltage divided on total width. Now let's go directly to exercise 7.4. Design a p-n junction to meet a maximum electric field and voltage specification. Consider a silicon. That's when we're dealing with silicon. This element is silicon. At T equal 300, that's mean room temperature, with a p-type doping concentration of Na equal to dot exponential 17. Here, this example is different because determine the p-n doping concentration such that Emax, absolute value Emax equal 2.5 dot exponential 5 volt divided on centimeter at a reverse bias voltage of VR equal 25 volt. Actually, this exercise is solved by the author. That means it's solved example, but I try to solve it by writing more details. Here, what the author wanted from us, he gave us the acceptor constraint, and after that, say determine the PN doping constraint such that means we don't have the result of donor concentration, and we have the Emax result. That means we can use the Emax equation to can calculate ND. Actually, I faced some problem by solving this equation because my result, it was not the same with the Arthur's result, because that if anyone can calculate it and help me to reach the appropriate or the right result, I will be very happy to that. Here, let's start from equation 7.36. Emax equal -2 electron bulk barrier potential voltage plus reverse bias voltage divided on permittivity, and this bracket all this force to have, and at the same all that to can calculate ND, to can calculate the result of donor concentration. Like the Arthur wrote, we can ignore the VBI if we do compression with the reverse bias. That means if the reverse bias bigger than the bulk barrier potential, that means we can ignore it because that will be if we put it or ignore it, that will be not big deal, because that, and at the same time we imaginate we know the result of bulk barrier potential, and his result is very small because that we could ignore it. Let's keep going. Here, equation 7.36 be like that, and all that to calculate the last result of ND. I tried to use this math tricks, but the last result was 8.43 exponential 15. But when I calculate all of that, I found another result because that I have mistake, but unfortunately I couldn't find my mistake. Why? I don't know. If anyone can calculate the result of ND, I will be very happy. Now let's go directly to exercise problem 7.4, the maximum electric field in a reverse bias. But here, the important thing we must know that here we're dealing with another element. That means another intrinsic carrier concentration, another donor concentration, another acceptor concentration. This element is germanium arsenide, PN junction at room temperature is to be limited to Emax equals 7.2 exponential 4 volt divided on centimeter. The doping concentration are ND donor concentration equal 5 exponential 15 and NA equal 3 exponential 16. What the author wanted from us, determine the maximum reverse bias voltage. Reverse bias voltage, that means VR. That can be applied. Because the author gives us the result of Emax, that means we can use equation 7.37, like I think, yeah, 7.36, or we can use equation 7.37. Yes, let's keep going. Like I said before, we must calculate VR max. by using 7.36. At first, I started to calculate VBI from equation 7.10, VT ln NA and D divided on intrinsic area concentration. Like I said before, we're dealing with another element. That means another intrinsic area concentration to germanium arsenide, not equal 1.5 dot exponential 10 anymore. His result is 2.1 dot exponential 6. The last result is 1.64. I'm sorry, because some trouble in the slide when I was trying to solve it by my hand. After that, I tried to use equation 7.37 to calculate the last result about VR by using equation 7.36. My result was wrong, equal minus 1.1, 639, and that's not appropriate. And I was thinking to use the equation 7.37 by calculate the total width, and after that, that will be easy. But I determine xn dot 485 micrometer, and by using equation 7.27 to calculate xp, and after that calculate all of them, the width was equal 565 micrometer. But after that, my result was not appropriate because it's different from the Arthur's result, because like I think it was 3.12 volts. If anyone can help me to calculate these two questions, I will be very happy. Thank you so much about your listening, your patience. Have a good day. I will see you in another lecture.